Oh, great. Thanks very much. Hi. So yeah, my name is Nicholas Matsakis. I work at Mozilla Research, and I want to talk to you guys today about the Rust programming language, which we're developing. Well, I shouldn't say we're developing it, because Mozilla Research is kind of spearheading it. But the truth is that without the community that we've got involved in Rust, we wouldn't be able to do nearly as much. So I'm really grateful to everyone. I don't know if there are any volunteers here, but to all the volunteers out there, thank you very much. And before I get going, I want to say two other things. First, I have stickers. If that appeals to you, come talk to me afterwards. Second, if you have any questions as I go, please feel free to ask them while I'm talking and not wait till the end, because a lot of the ideas I'm talking about kind of build on one another. So if you get confused in the beginning, it could be easier, or the rest of the talk might make more sense if we clarify it first. The first thing I want to answer is the question I get asked first. When I say that I'm from Mozilla Research and we're working on a programming language, most people say, kind of, Mozilla, what? I thought you guys made Firefox. Why are you working on a programming language? And the answer is that, first of all, yes, Mozilla has a research arm. And our goal is to kind of look at what we can do to make the web model more successful and make it apply to more things. So things like ASM.js, Firefox OS that were mentioned in the introduction, those came out of Mozilla Research, actually. Well, to some extent, or collaboration with us. And another thing that we're looking at is what can we do just to re-architect the browser itself? So not just HTML and CSS and expanding the scope of those, but the browser itself, the basic design hasn't really changed a lot since Netscape days. And computers have changed a little bit. We have multi-core now. We've got a lot more capacity. And web pages have changed a lot. So we're hoping we can improve security and performance and get a more parallel browser architecture. And that's a project which we call Servo. But part of that question is, well, if we're going to rewrite the browser core, what language should we do it in? Right now, if you look at every major browser, they're written in C++. And not just a little C++, but like millions and millions of lines of C++. I think Firefox's repository has 8 million lines or so. And the reason for that is that C++ gives a lot of control. And browsers are, in some parts at least, pretty low-level programs, similar to operating systems in some regards. And they need that kind of control to get good performance, to make sure that when you scroll, it doesn't jank around and move in kind of an uncomfortable way and so forth. And the problem is that although it gives us good performance, C++ gives really no safety guarantees. So when you have 8 million lines of code, you can bet that somewhere in there is more than a couple of seg faults and security vulnerabilities and so forth. And so that's kind of a good reason why not to use C++. But maybe there's another language out there. Why do we have to make our own? Right? And the problem is that most languages that are out there fall along a line like this. They kind of trade off control and safety. So for C++, you get a lot of control, but not a lot of safety. And then you have on the far extreme on the other side something like Haskell, which gives you a whole lot of safety, but very little actual control of what the machine is doing. You have to know a lot of, the compiler will do a lot of fancy tricks, and the runtime does a lot of fancy tricks to make it run fast. But if you, as the programmer, want to get control, it's a much more complicated process. And in between, I think most other languages kind of fall somewhere along this line. So you have something like Java, where you have a lot more control than Haskell, but you still have this runtime in the background and so on. The idea of Rust is to say, can we just step off this line altogether? Can we have the same control, or similar, as we get in C++, but with the same kind of safety guarantees that Haskell gives us? So no seg faults, no data races, no overflowing arrays, and that kind of thing. And so the purpose of this talk basically is for me to convince you that yes, we can, and show you how we're doing it. And to begin, not everybody knows C++, I guess, presumably. So I will just kind of give an idea of what I'm talking about, make it more concrete when I say control and also safety. Right? So here's a little fragment of C++. And the first thing it does is it creates a hash map. And one of the nice features of C++ is you can put this hash map kind of on the stack. And we'll see what that means in more detail in a second. But basically, it means that when this function returns, or this block exits, we know deterministically the map is going to get freed right then. Right? And that's good for keeping memory usage down and so forth. It's just efficient in a lot of reasons. And another thing C++ does is let us take pointers right into the middle of data structures. So if I fetch an item from a map in C++, this lookup, it doesn't copy the data out of the map. It gives me a pointer right back in the middle. And that means if the value that I'm putting in this map is big, that's a better way to do it, and I don't have to have layers of indirection and so on. But I can make some really trivial mistakes. So here I'm going to take that pointer right into the middle of the map, and I'm going to return it to my caller. And the problem is I just told you that the map is going to get freed as soon as my function returns. So now I have a pointer into freed memory, and I'm returning it to the caller. And that's a recipe for disaster, right? So let me I'm going to do this sort of stepping through the execution a couple times in the talk. So let me do it here for the C++ to reiterate what I just said. So what that program does, the first thing it does is it creates a map. And in fact, the data is not all on the stack. It's actually split between the stack and the heap. But you wind up with the fields of the map on the stack, and the data itself is on the heap because it needs to grow and resize and so forth. And then we create a pointer right into the map. And you see what I mean. This is a single pointer, and it goes directly into the heap there. And then finally, we return that pointer. So what's happening now is that pointer got copied from the topmost stack frame into the caller. And then we're going to free the topmost stack frame and all of the data that it owns. And when I do that, now you see this pointer here is just pointing out into that grayed out, hopefully that works, yes, OK, that grayed out space. And that's what we call a dangling pointer. And that's a really bad thing, because later, when later allocations occur, that memory might get reused. And now I have a pointer into some other memory, which wasn't even originally, which contains some other data that may not even have the same type as what I had before. And that's a recipe for crashes, but also security vulnerabilities, and so forth. So what it comes down to is that C++ has a lot of safety rules that you have to obey. They're not all written down, or at least not in a simple way. And if you don't get them all right throughout your entire program, every line of those 8 million lines, you have a problem that can crop up anywhere. So it's kind of like this house here from my view. Each of those bricks is a piece of memory, and if you just have one that's taken from the wrong place, the whole thing can come crumbling down, right? So what do people normally do? In most languages, they will use a garbage collector to solve this problem. And that is a great solution a lot of the time. But the problem is, in some particular spaces, a garbage collector isn't so good. So what a garbage collector does is, instead of freeing the memory manually, it'll basically just periodically search through all of the pointers you have and find all the memory that you don't have a pointer to, and it'll free it then, right? The problem is that this introduces overhead. It introduces kind of unpredictable pauses. And there are various ways to address this by making interruptible garbage collectors and so on. But nonetheless, you have this runtime in the background. And that makes it really hard to integrate with a lot of other languages. So one example is just taking a library that requires a runtime or a garbage collector and using it with some random C program is a little bit difficult. But it's also hard to integrate with other virtual machines, and especially with other garbage collectors, like, for example, the one in JavaScript, right? So since we want to write a browser, we have to worry about that kind of thing. And this is just not really the best way to go about it. So what we've done in Rust is take a different approach. Essentially what we said is, let's take that same C++ and all those safety rules that you were supposed to be enforcing, but you weren't necessarily doing it, and let's have the compiler enforce those safety rules for you. And the compiler is going to be pretty rigorous about it, So basically, it amounts to coming up with a set of conventions that guarantee that you're following all the rules you're supposed to follow and enforcing them in a religious, sort of rigorous, strict way. The advantage of this is you don't need a runtime because you're not making the mistakes that the runtime was supposed to catch for you. So to be fair, I called this the Rust solution. But really, the Rust solution is taken by bits and pieces from lots of other languages and a lot of academic research and so forth. So I think the biggest influences are probably C and C++, of course, Haskell and Erlang, and Cyclone, which is an academic language. But I think those of you who know a lot of programming languages will see things that you recognize as I go along. So in summary, if you take one thing away from this talk, I would like it to be this slide, which is that the goal of Rust is to support the patterns from C++ that you know and love, like pointers into the stack and into random data structures and so forth, but without all the bugs that make you pull your hair out for 3 days and that only crop up when your customers are overloading your website or whatever. And we want to do that without requiring a lot of runtime, in a way that basically is as flexible as C. So that means we could use Rust, for example, to implement a kernel. or to implement a library that plugs into some other program, an embedded projects, things like that. Now there's one caveat I have to point out. I say that we prevent all these horrible bugs, and we do, except if you link to C code, well, we can't help you. You got C code going, you could do anything. And we also have this thing called unsafe code that I'll talk about, which lets you basically break the rules. So you might think, well, what kind of guarantee is that if I can just break it? And the answer is, as long as when you can confine the set of code that might break the rules down to like 1,000 lines of code or 100 lines of code, it's much easier to review it and read it carefully versus if you have to search every one of the 8 million lines, right? So there's still a big advantage here. So this is what I'm going to talk about in the talk. The first section is kind of Rust memory management strategy. The second section is how we do parallelism. And the final one is a little bit about this ability to break the rules. And what I'm not going to talk about is a kind of comprehensive overview of Rust syntax or some of the fancy features that we have. But suffice to say, we've tried to take a lot of the niceties that you may have found in other languages, like pattern matching and so forth, and we tried to offer those too, just to make everyday programming a little more pleasant. And one of the things we do offer, or at least plan to, it's still being hacked on actively as we speak, is an optional garbage collector. Because I spent some time trashing garbage collection, but the truth is it's often very useful. It's only in certain contexts where it's really not what you want. So we try to make it optional and on a per thread basis. So you can even have like one thread, maybe your compositor thread or something which needs a much more precise timing guarantees, and other threads that don't have that requirement. So let's talk about memory management. Basically, you have this control and safety dichotomy I talked about, right? So the way to get the most control out of your memory management is probably something like malloc and free. It's pretty flexible. You know exactly when memory is getting freed. It's when you called free. But it's pretty risky. If you do it wrong, if you call free 2 times or 0 times or whatever, you get a lot of bugs. And then there's the garbage collector on the other side, where you don't really know when memory is getting freed, but you don't have the opportunity to mess it up. So what Rust does is to say, let's keep this kind of malloc-free model, but let's put a build on top of it a set of conventions that make sure you're doing it in a reasonable way. And we call those ownership and borrowing. So I think ownership is pretty analogous to real life in some ways, at least a kind of weird version of real life. So to help me explain it, I'm going to bring in my handy stick figure friend here in his little book, right? And basically this book, it kind of represents a data structure. Okay? So if you think about ownership and a book, if I have a book, I have it in my bookshelf, I own it and other people don't, right? So basically if they want to read that book, they have to come to me first because it's in my bookshelf. They can't just have their own copy floating around, or if they do, it's a separate book. Well, it works the same way with a data structure in Rust. So if I have like a hash map or something, and I'm a stack frame, let's say, I own that hash map. I know that there are no other aliases to it. Nobody else has that same map, right? And that has some nice implications. For example, I know I can just free it anytime I want to, because nobody else has a pointer to it, so they won't have a problem if it goes away, right? And in fact, I don't even have to do it explicitly. I'm the only one that has that map, so when I'm finished with it, when I quit or return, we can just free it, right? I've always wanted to use that fire transition, and I never had a justification. But so that's basically how it works with data structures and memory management. But the other thing I can do, if I own something, is I can give it away, and I can transfer it. So I might give my book to you. And in that case, once I've done that, it's yours now. I don't have it anymore. And because it's yours, if you are finished with it, you can free it, right? You're the owner now. So let's look at some code and see what I mean. This is a little bit of Rust code, and this actually would not compile, and we'll see why later, or in a minute. But let's kind of step through it. And the first thing it does is it creates a hash map. And for those of you who know C++, you'll see the word new there, and you'll think memory allocation. It's not a keyword in Rust. It's just the name of a function that, by convention, returns a new hash map. But basically, what we're going to wind up with is exactly that same setup we saw from C++. We'll have the fields on the stack and the data in the heap. And now we can call this function take. And you see I'm giving the hash map as argument. What that does is it transfers ownership. So basically, I'm going to push a new stack frame, and I'm going to copy all the fields from the parent, or the caller, to the callee. And this is where real life and computers kind of diverge. Because if I didn't do anything else in a computer, although I gave ownership to the call E, I still actually have a copy on my stack, right? That's kind of why DRM has such a hard time. But if I want this to work more like real life, in Rust, that's how we want it to work, is when you give it away, you don't have it anymore. So what we do is we just kind of forget about it, right? The compiler will enforce this, as we'll see. But basically, you say, OK, you've given this map away. You can't use that data anymore. So it's as if you didn't have it on your stack. It's been transferred to the caller. And now because the function take owns it, the function take can go and do some stuff to the map. And when take returns, the map's going to get freed, because take is the owner. And so we'll be returning now to the call to the original function. So the only difference is we don't have the map anymore. And this is where the error comes in. So if we tried to use it again, we would get a compilation error right here. The compiler will say, no, that variable m, you moved it already. You can't reference it anymore. So that's all good. But sometimes, I have a book, and I read it, and it was nice. And I'm not really done with it, but I might think my friend might like it. So I could give it to them on the agreement that sometime later, they're going to give it back to me. This is called borrowing, right? It's kind of a convoluted explanation. But it works the same way with data structures, if you think about it. Like maybe you have a hash map, and you didn't mean for that function that you gave it to, you have some helper function, you didn't mean for them to free it. They were just supposed to read it for a little while, insert some entries, take some entries out, and then you want it back at the end. So we call that the same thing. You don't have to give data structures to the caller, to the functions you call. You can lend them out. And the main point that's most important, what separates Rust from other things, is that these temporary references that you use to give temporary access, they're a different type from other kinds of pointers, and they have a lifetime, which is basically the span of time in which they are valid, right? So I lend it out to the helper function. If the helper function is going to use it in return, the lifetime might be the time it takes for that helper function to execute. And most importantly, the compiler, let me step back. Let's go back to real life for a second. If I've lent my book to a friend, I haven't given it away, but there's still a little bit different from not lending it, right? It's not in my bookshelf. So there's some things I can't do. Like I can't throw it away. I can't give it to somebody else, not until I get it back. Well, it's the same way with these data structures. When I borrow it out, if I have a helper function, while that helper function is executing, there are some restrictions on what I can do. I can't trash the map that I lent out to them. So let's see the code, and I think this will make more sense. Here's a little fragment of code. It begins just like the other one. It creates a hash map. But the next thing it does is it takes the address of a local variable. So if you know C, you'll know the ampersand operator. But if you don't, what that basically does is it makes a pointer right into the stack, right? And this is what a borrow is. So that sounded a little abstract before. More concretely, a borrow is taking the address of something, basically. And the lifetime of this borrow, that span of time in which the data is borrowed, is going to be from the point where you took the address to the point where the variable went out of scope, the variable b. So basically till the end of the block. And the compiler is going to check. It's not legal to lend something out for longer than it exists altogether. So for example, if we tried to borrow this hash map for a span of time that was bigger than this current function, that would be an error. We'll see that later. I'm getting ahead of myself. But taking the address is one kind of borrow. It can also be a little bit more indirect. Like I told you that in C++, when you fetch something from a map, you get a pointer directly into the map. Well, in Rust, the same thing happens. So if you look, I changed it. If you call m.get, that's going to make a pointer right into the map data, right? And this is actually a kind of borrow as well. It's the same exact thing, basically. I took the address. In the first case, I took it of the m variable. In this case, I took it of some data that the variable m owns. But either way, we've basically borrowed the map. And do I have a little thing? What's going on? OK. Anyway, so let's see now. What does it mean? So I said that there's the lifetime of the borrow. So the map is considered borrowed until the end of the block. What does that mean, really? That means that there are some things we can't do with the map anymore, right? Kind of like our book. So one thing we can't do, well, this isn't with the map, but one thing we can't do is return that pointer, that borrowed pointer, out to our caller. We'll get an error here. And the reason is because that would exceed the lifetime of the borrow. We only lent it till the end of the block. So you can't just have that pointer go off and escape. That would break the whole idea of borrowing. When you borrow something, you have to give it back, basically. And this would be not ever giving it back. So we'll get a compilation error. And that's exactly the bug I showed you with C++ in the beginning, right? But there are some other things we can't do that would be bugs. Like we can't call that function take and give it the map. Because that would actually, if you recall, that'll free the map, and then we have this pointer into freed memory, and that's bad. But that won't be allowed either, because that's transferring the map, and the map is considered borrowed, and we can't transfer something while it's borrowed. So we get an error there too. So basically, the memory management strategy is, that about sums it up. Essentially, you have for every data structure an owner. It moves from place to place, and the owner can free it, or they can just keep passing it along. And then you can take these temporary references. And while something is borrowed, you can't free it. And you also can't have that reference get used for an indefinite period of time. It always has to be blocked by some specific lifespan. All right. So the next thing I want to talk about is parallelism. And we'll see that our approach to parallelism really builds on that ownership, those ideas of ownership that I just talked about. But I think everybody kind of knows now that parallelism is important and we can't ignore it anymore, and there's some graphs that go like this and blah, 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 and Moore's law. So if we can all agree on that, then I can say that we also all know that parallelism is pretty hard, right? Like if you think getting your memory management stories sound is hard, parallelism is even harder. And so it'd be really good if we didn't have to worry about some of the nasty bugs that come with it, particularly data races. And what a data race is, for those of you who don't know, is let's go back. Basically, it's two threads writing to the shared memory. It's not the technical definition, but it's pretty close. So if you imagine I have these two guys, and these two stick figures, and they both have the same book. If they try to write on it at the same time, they're just going to get some gibberish, and it's going to be a mess. And what we want to do then, if you have a successful project, is you don't allow that to happen. And you can do that either by not writing to the book at all, just reading it, that's pretty good. Or you can take turns, which is what a lock is for, right? Basically say, OK, I'm going to write to it now. And then the other guy says, OK, now it's my turn. And the lock makes sure that those turns, everybody plays fair. The problem is, it's just like memory management. That's really easy to say, right? That sounds, it doesn't sound so hard. But in fact, if you have 8 million lines of code, it's pretty hard. Once in a while, you forget that some memory is shared, or you don't realize it's shared at this particular moment in time, or whatever. Or worse, it was fine, but then you quit the company, and some other buddy comes, and he doesn't know what's shared and what's not, and he makes a mistake. So basically, we would like to do better, right? So if we go back to our control and safety, if we have shared memory, this is the control option, right? And it's great. But there's really no way to avoid these bugs except being really, really careful. And if we go the other way, we have these things like actors, which are also really nice when they work. And what they basically say is, let's avoid data races the easy way. Let's just say you don't have shared memory at all. Voila, problem solved, we can all go home. But sometimes that's not enough. Sometimes you do want shared memory for performance or whatever. And so what we say in Rust is, let's start with the actor idea. Let's say most of the time we don't have shared memory, because that's actually pretty good, and that gets you pretty far. But when you do need it, we allow shared memory, but only via these safe mechanisms that guarantee that you're taking turns, or guarantee that you're only reading, and so forth. So here is my stick figure explanation of how it works, and then we'll get to the code. Basically, like I just said, the default is that you don't share memory. So if there's one thread here and it has 2 books that it's working with, and then another thread starts up, we can transfer some of that memory over, right? And this is that same notion of ownership that I just talked about. So we're basically just giving that thread unique access. And similarly, we can use this idea of messaging. I'll show you in a bit. But basically, you can create data structures and then send them back. And it works the same way. The memory is always transferred. Nobody ever has the same data at the same time. Right? So let's take a look at some code. This is the code to start a thread. It starts by creating a hash map, and then it calls spawn. And what's spawn? That's a little library routine that starts a new thread. And it takes as argument this thing called a procedure. If you know what a closure is, a procedure is kind of like a closure. It's a function body bundled together with all the data that that function is going to use. The difference is between a standard closure and a procedure is that a procedure really owns that data. So nobody else has it. Right? So basically it looks through, finds the local variables that appear inside this procedure body, and it moves them into the child thread. So let's do my favorite graph here. Yeah?
How is the thing that you just described, how is it different from a class?
From a class? Well, it is kind of like a class, actually, with a single method, essentially, like call. Anyway, so it's basically, yeah, it's like a class with a single method. That's another way to look at it. So you have, here we start out, we've created this hash map, and then we're going to call spawn. And this is the body. That's the body of the procedure I showed you, just kind of pulled apart because it's going to be a different thread. And the point is the child task takes this message m, or this hash map, and moves it over, right? And most importantly, the parent doesn't have it anymore. There's no sharing going on. This is an atomic transfer. And we can use, let's see how much time I have left. Oh, okay. I'll go through this fast because I'm running a little short on time. Thought I had a little more, but that's all right. This is another useful thing that, for example, Erlang has that's really handy, is this ability to send messages between threads while still maintaining no shared memory. And it's basically like a pipe in Unix, right? So you create this channel and port pair, and they're kind of quantumly entangled so that anything that you send to the channel, ownership transfers over to the port, and you can use this to communicate. So let me show you an example. I think it'll be pretty clear. The parent thread starts out, and it creates the port and channel pair. And right now, the parent thread has both the port and the channel. So that's not that useful. It could send messages to itself. That, I don't know, could be nice. But then it spawns off a child thread. And that child thread takes the channel, but leaves the port behind, right? So now this is the magic part. The channel and the port are split across the two threads. And now when, at some point later, that child task should execute, it can create a message, and it can call this send routine, which is going to transfer the ownership of the message out of the child into the port. And then later, they're asynchronously executing. When the receive function is called, it'll transfer the message over from the port into the parent. So you see that we sent the message, we moved data around, but we never actually had access at the same time. So what if we did want access at the same time? The trick, basically, as I said, is to take a data structure, that is to take that memory and just make sure that we're using it in the right way. So we would either like the memory to be immutable, so that nobody can be writing to it, or to make sure that we have a lock, and not just some lock we should get, but a lock we have to get, so that we know we don't forget. And the way that works in Rust, I'm just going to talk about the immutable case, just for time, is basically to build on this ownership idea and introduce some library types. So we can, this is actually an extensible set of things. These are the two we have now, but you could build other strategies. And these library types are called arcs, which stands for atomically reference counted. I kind of like to picture them as like Noah's Ark or something, but basically it's a data structure that owns some data and then uses the API to only give access in the way that we want. And because the data structure owns, because the data is owned, nobody else has it, right? That's what I said in the very beginning. So here's an example. I'll skip over the introductory part, but we can get to this state where we have two threads. They each have an arc, which is pointing to the same thing. That's the kind of yellow box in the middle. And inside that arc is a hash map along with a ref count. Now the ref count is 2 because there are 2 of them. And yeah, you see multiple threads have access. Okay. So the parent thread can use, basically the only method that arc offers is this thing called get. And get is going to create a pointer at the data that's inside the arc, and it's going to return it as a temporary immutable reference. This is borrowing, but borrowing the contents of the arc, essentially. And now because that reference is immutable, if I tried to insert into the hash map, I'm going to wind up with a type error because I'm trying to mutate something that's immutable. But I can fetch things out of the hash map. That's just fine. So that'll create a pointer, right? So that's the Rust strategy in a nutshell, is that we start out with a basis of no shared memory, using ownership to move things from place to place. And then when you do need sharing, for whatever reason, we build up a library of safe, essentially, containers that encapsulate some protocol, like read-only access or acquire a lock, and so forth. Okay, so that's all pretty good, but sometimes, you know, it's not enough. Sometimes we got to break the rules a little bit. You know, for example, some of you might have noticed that I said all data has one owner. I said that a lot, actually. And then I showed you this arc with 2 owners and a reference count. And I kind of papered over that, but you know, you might be wondering how that works. Well, the answer is that the implementation of arc bends the rules. It uses these things called unsafe pointers and unsafe blocks. And an unsafe block looks kind of like that. It's got some code and the word unsafe. And what it means is, hey, hold on, I got this. You know, you don't have to check this code very carefully. You can just trust me. So basically, the compiler will suspend the rules. It will let you do things. It's essentially a different syntax for C, more or less. You know, you can copy pointers, you can make aliases. And the idea is you should do that, but you should, when you're finished with the unsafe block, you should kind of put things back into a state that's safe again. So essentially what we're trying to do here is give you the means to build new, safe abstractions. And by safe, I mean even if the caller does some goofy stuff, like calls all the methods in all the wrong order, it still shouldn't crash. It still shouldn't cause data races, and so on. So something like arc that I showed you that has exactly one method that gives you an immutable reference, that's a safe API. There's really nothing you can do with that will break any rules. And we use this sometimes because we need better performance. So there might be some little method like operating on a vector or something that gets called 10,000 times, and we can write it in a more efficient way if we can bend the rules. Okay, that's a good trade-off. We can read it very carefully, and that's fine. Or we can build new things like arcs and the task library itself, for that matter. So that's about it, basically. In short, I guess, as I said, the one message I want you to take away is that Rust is kind of an opinionated version of C++. You know? It's like you take all the things that you used to do in C++, but do them in a particular way, kind of like a strict code reviewer. And the thing you get out of this is you get safety, but you also don't need to have a runtime. So I went over memory management, and I went over threading. And in particular, I went over a little bit about how unsafe code can let you build up new abstractions. So if you're interested, you can find more information. That's our website, the IRC channel, and the Reddit, whatever you call that, subreddit, I guess. And thanks very much. Any questions? Yeah?
When I started to learn Rust, the tag I checked out was the first one after managed pointers or arcs, whatever, had been removed from the core language. And that was quite confusing. Can you suggest a good way to stay on top of the language since it's changing so quickly? Because all I could find was some kind of blog posts from a few months ago talking about how it would happen. It didn't seem to be a kind of central
Right.
place for the development.
Yeah. So the question is, basically, Rust is changing really fast, and how can I stay on top of those changes, right? And that's a good question, and the answer is twofold. One is we're going to slow down. So it's been a long, long road. I mean, I've been working on this for 2 years now, and it's been a project for longer than that. And we've done a lot of iteration, but we're kind of happy with what we've got now. Though we are doing we're paying off some technical debt, kind of like managed pointers, doing some changes that we've postponed for a while and saying, let's get them done. The goal is that this year we should release a stable candidate that has kind of a core language that won't be changing anymore and build on that. I think that I don't know that there is a good central source of information for tracking except for the IRC channel for asking questions, and there's like a This Week in Rust, but it would be a good thing to create, is the truth. But hopefully it will be less and less necessary, essentially. Yeah? So the question was, why don't I just use boost shared pointer and go home, right? And I think that's a pretty good question. I don't think it's an unfair criticism nonetheless, both because there are a lot of code bases out there that don't necessarily use boost for everything, and because, well, things like data races and so forth are much harder to avoid. But nonetheless, it is true, there's some truth to say that C++ has all these tools to build abstractions too, and if you're very rigorous and you use those correctly, and only those, then you can still get a lot of the benefits of Rust. Rust is kind of a nicer, from my opinion, syntax on top of the, taking those strategies and making a language out of them, rather than making it a particular way of using C++.
Maybe a comment further than a question, but it seems like some of the features that you described, mostly earlier, can be implemented by a standard C or C++ compiler that wants to be a little bit more helpful without any new syntax or anything else.
The question was, can you implement this as a standard C++ compiler, like a lint, essentially, right? And I think the answer is, some of it, yes. It's kind of the same as before. You could, but some things are a lot harder. I mean, aliasing relationships in particular are notoriously hard to track down. So I think you'll find that you could do that. You won't be able to compile existing C programs with that because they weren't written with that convention in mind. But yeah, that would be an option, I guess, in theory. I guess what I'm saying is, I think you could do that, but it would be sufficiently different from C as to be a new language anyway. Yeah?
Can you use the MM system called reasonably? As far as I understand, the unsafe blocks, of course, can access that memory, but wouldn't it spread out to other parts of a larger project? Can you intermix different types of memory? One's controlled by,
Yeah.
for example, by MM, and one's controlled by the compiler.
Okay, so the question is, can I intermix different kinds of memory like mmap and so forth? And the answer is absolutely yes. That's one of our big goals, is to support, essentially, we borrowed the term from C++, but kind of smart pointers. And these are basically these pointer types can manage memory in different ways. So we have things like an arena, for example, that allocates a big block of memory and then doles it out and then frees it all at once. You can implement those kind of APIs, and you can implement them safely for the most part. I don't know, what specific use case you have in mind for calling mmap. Certainly you can call mmap and get back some raw pointers. Making sure that it's safe is a little trickier, but I think it would be doable. Oh, well, yeah, sure. To map an input file or something, yes, that you could certainly do that, right? I mean, I think if you call mmap and then you have this pointer that represents a file, there's some. You have to sometimes work a bit to make sure it's safe if you really want that. I mean, you can take risks yourself. It's your project. Like, you could just pass that pointer back and then hope that nobody calls munmap, right? But you can also do things like have an object with a destructor that calls munmap. And to actually get access to the pointer, you have to go through that object, kind of like arc. And in that way, if you never call munmap directly, you're guaranteed that the memory is still valid as long as someone is accessing it. So we have the tools to build that kind of thing. Get reasonable guarantees. Yes?
So relating to that, I guess outside of the unsafe block, you can make only the calls, pure calls, as in like calls with the language, and if you want to make like external syscalls or something, you need to make them inside the unsafe block itself.
Yeah, calling C code is considered unsafe. Yeah. The question was, sorry to repeat it, but when can you call system calls and so forth? So I think this guy's had his hand up a while. So what have we built with Rust is the question. And the answer is, first of all, the Rust compiler itself is self-hosting, which means it's written in Rust, and then you just compile each new version with the old version, which sometimes makes for a really fun time when you have a bug that you didn't know about for a while. But that's a pretty big program. However, we're also working on that servo project I mentioned earlier, which is kind of a rewrite of the browser. And then there are a lot of independent projects that I don't even have a full handle on. There are even a few people putting it into production, which I think is interesting because we're still making some changes, but they're willing to keep up, So that's all right. Good for them. Yeah.
In terms of the evolution of C, the C language, I guess, over time, would you see Rust fitting in as a divergent fork or sort of the next step or somewhere in between?
Where do I see Rust relative to C? I don't.
C, C++, the C-based languages.
I mean,
divergent from C++ over time, or?
Yeah, I mean, so the question is, well, what's the relationship, I guess, more or less, between Rust? Do I see them as diverging? I think Rust is a different take on C and C++. So we aim to, not to replace C. I'm not that ambitious. That would be pretty impressive. But to give you another option that whenever you might use C or C++, you could use Rust, and you would get better safety. But the languages, it's not like the syntax and the semantics, I think, are sufficiently different that you can't really call them the same language. But they have a lot of similar aspects. Yeah? And maybe. Okay.
Sorry.
Oh, that's fine. Go ahead.
Comparison between Go and Rust.
Right. That's a good question. I'm surprised it took this long, actually. So I'll start out by saying I think Go is an excellent language. We're both kind of targeting, in some sense, similar things, but in some sense very different. So Go is, at least initially, I don't know if they still do, called themselves a systems language, and Rust calls itself a systems language. I think the systems that we're talking about are kind of different. I think Go more or less falls on that spectrum that I talked about between control and safety, that trade-off, somewhere between Java and C++, I would say. Gives you a lot more control, but it also does have things like data races and so forth that are safety. So it gives you more control than Java, but still less than C++, and it admits various errors. And that's not a bad thing. I don't mean, when I say you're trading off control and safety, I don't mean to criticize all the languages on that line, right? There's a reason they're all there. Language design is like this subtle game where everything you change has costs and other benefits, and I think that line is kind of a sweet spot in one degree. But sometimes it's not a sweet spot for some applications, and that tends to be where C++ gets used, and that's why we're trying to offer an alternative, right?
So Rust is obviously like a fairly emergent / new language, but in terms of like performance analysis and comparison of the efficiency of runtime and stuff like that, has there been a lot done into that, or not particularly at this stage?
So the question is, how much comparison have we done for the performance of Rust? And obviously, I made some kind of strong claims about control and efficiency, and probably a little stronger than were warranted by the full set of benchmarks I don't have to show you. But the answer is that I think every time we do some comparison, we usually find that the code is pretty comparable to C++, although there is often most micro benchmarks are actually benchmarking some library, and our libraries haven't been optimized that much. So a lot of times it'll be, like I think one particular one I remember was the function that converted numbers to strings was not particularly efficient, and there was a benchmark that basically wound up calling this function a whole lot of times in a loop. And we looked pretty bad until we improved that function. But in terms of the raw, kind of the LLVM code that we generate, I didn't mention it, but we build on LLVM. It's pretty comparable to C++, and I think there's no reason that with enough tuning we can't have performance that is in the same ballpark. And we usually do, I should say, at this point. Like our hash maps and data structures are pretty fast because they have received a lot of attention now. Is that it? Okay.
Well, I think we're just about out of time, but if anyone has any more questions, I've got a couple of them. It's lunch now, so maybe we could answer a few more. But
That's right. I'll be here, and as I said, I have some stickers just burning a hole in my pocket.